It's that time again, boys and girls. Tweet, you. Yeah, look at you. So excited. I mean, things I would know if I were you. One, momentum. I mean, that seems a little on the nose, but this means individual momentum. What is it? How is it calculated? How is it calculated is the simplest thing in the world. What it is definitely the challenging part of this chapter. Okay. Number two, impulse momentum theorem. Number three, conservation of momentum. Momentum, both 1D and 2D. And finally, number four, types of collisions. Questions? Today is all about questions. Yeah.
How do you, so on the review for 6.6,
Uh-huh.
it's asking you to find the force of like the jello on the rock.
Mm-hmm.
How do you find the individual force of that?
It's just so we did one similar to this on I think it was in the impulse momentum theorem. It's the idea of dealing with individual forces rather than the total force, and it's the exact same way that you've always done it. It's not any different whatsoever. So in other words, we did this problem with a car early on. I think it was the I think it was impulse momentum theorem, but let's check. Go. There it is. In this problem, a car's traveling down the road at 25 meters per second east. The engine's pushing forward with wind resistance, aka force friction. Sorry, engine pushing forward, and wind resistance is such and such. Okay, tells you the mass, blah blah blah. Point is, usually what we've been doing in this particular case is I have just told you in a lot of the easier problems, I've said, hey, here's your sum of forces. Okay? So this is getting into this idea of pushing away from what you've necessarily like this like plug and chug methodology and starting to get into what it really means. Okay? What are sum of forces? Okay? Well, what's happening, what you would usually do is you would usually draw that picture and kind of getting used to this, you'd say, hey, force of gravity is down, force normal is up. Now, those are actually a vector addition between those two, right? Okay, it's a vector addition between those two, except since they're the opposite direction and since they're equal, what does that vector addition end up doing? Canceling each other out. Now, we show this specifically in previous chapters by doing this. By saying acceleration is zero, this ends up looking like sum of forces is zero. Now, sum of forces is zero is a vector addition. You're used to kind of in one dimension, in which, hey, here's a force, and it ends right back at the beginning. Okay? We just don't worry about kind of drawing the thing like that. We just know that they're balanced in the y up and down because it's equal to zero. So let's keep it simpler. Just worry about the y. Okay. In this particular case, we have force gravity down, force normal up, again, canceling. In this example here, I think it's a little bit different than the one that I've said. You know that if the net force is that way, then what's the object doing? Accelerating that direction. Okay. Now, whether or not it's speeding up or slowing down depends on its initial velocity. Based on how I drew this, you'd probably imagine that the car is probably traveling that way and it's going to slow down, right? How would you draw that here? You would draw force friction back, and how big should force friction be? What's that? Larger than. All right. So let's get into this right here. How does this show down here? Well, that is this bit right here. How did I draw that? This amount is equal to that amount, right? This piece right here. So the extra is what causes acceleration. The extra is what causes acceleration. So what you would typically do, if I gave you a situation like this and I told you a net force was, say, just making something up real quick, 200 newtons left, real quickly you would just take that and plug that in there, okay? What would you do if this was your picture in that setup over there? Well, you would first thing you would do is ask it is accelerating. And you know it's accelerating because obviously there is unbalance, because it's slowing down, all of these things. So what does that mean here? Well, the very next thing you would do is you would say this is force of engine minus force friction, with the solid understanding that more than likely, well, not more than likely, this number is definitely bigger than this number right here, right? So if I put some fake numbers in here and I were to tell you, let's do this, you know the total is 200 left. So if I told you that the force of engine on the car was 1,000, quickly tell me, what is the force of friction in this case? Negative, yeah, well, let's see, yeah, 1,200 to the left, right? So it's just understanding how these two are interrelated. Now, from a practical standpoint, how do I tackle this problem? Easy peasy. If it's 200, if it's total, plug it in. If it's not, literally do what we did right here. Plug in the individual forces. So instead of sum of forces times time equals change momentum, it would be force of engine minus force friction, which you'll remember is still negative 200, right? Times time equals change in momentum. And if you want to manipulate your variables in this particular case, I'm going to divide by, like I say, I was trying to find force engine, or in your particular case, force jello. Okay, you would divide by time, and then add force friction on both sides. And why does that work? Because here's what we're saying. The extra bit is a certain amount plus force friction. Why plus force friction? Well, let me change my numbers again to make this a little simpler. Actually, not change my numbers, just change the direction. Let's say that force engine is that 200 to the right now. And again, let's actually go to, let's make something up here. Force friction is now 400 newtons. How much is force engine? You can do this in your head, but what is it? 600, right? Just to get that extra is 200, and that's all this math says. Literally, that just did what you did. What's the extra? 200. Add 400. Why? Because it's got to be at least 400 plus the extra gets you how much force engine is at the end. But again, I apologize for this long explanation to a short question, but the ultimate goal that I had in this long explanation was to try to get you closer to using your understanding of forces to answer this question yourself, right? How do I deal with total? How do I deal with individuals? Hopefully practically the exact same way. And then conceptually, like I said, either plug it in or just replace it with the individuals. In your particular case, I believe this will be jello up and gravity down. Yes? Do be very careful on that particular problem. You just have to use, I think it's somebody dives in here. Let's just dives into some jello, right? Okay. Keep in mind up here is different than down there. On the top part, you're just going to use straight up kinematics. Why? There's only acceleration of gravity. You can find the speed, right? But also, the initial and the final of that top part then switch when you're down here. When you use the impulse momentum theorem inside that jello, should you have a velocity when the person hits the jello? Yes. Would that be the initial or the final for this section? Initial, correct. Right? And then, of course, you'd expect the person to stop in the jello, right? Which means final momentum is 0. That messes with people because this final right here of this section, of course, becomes the initial of that particular spot. Just make sure that when you're using the impulse momentum theorem, that you're being careful with when you are using it. I'm using it once, it hits the jello, so initial should be the moment it hits the jello, and final should be that end spot within jello itself. So actually in this particular setup, the most important thing is to get that is 0, and there is still a negative right there. The reason there should be a negative right there is quite simple. Well, relatively simple. There should be a momentum when it hits, right? So to get the momentum back to 0, the change in momentum has to be that way. Meaning, if I have a negative momentum initial, the change in that better be positive to get back to 0. How are we doing? Okay. Other questions? Sure. Would you like it 1 dimension or 2 dimension? Both. Okay. You want elastic or inelastic? Perfectly inelastic. What's that? Elastic. Okay. So we have. Let's do something simple to begin with, and we can make it more complicated if you'd like. Okay. So here is the cue ball that is going to run into the 8 ball right here. Okay. Cue ball has a velocity and the 8 ball doesn't. Okay. This is very, very simplistic, so I apologize. But now I've drawn the velocity. Technically, the momentum is that multiplied by mass, which won't change much in this particular case because ideally in pool, both objects have the exact same mass or pretty darn close to. So we'll enhance it just a little bit, but here we go. Here's the momentum of the cue ball initial. The way you draw this, how I typically draw it, and you can draw it from either direction, but I usually start with the initial. So, and what's the momentum of the cue ball, the 8 ball initial? 0, because it's not moving, so I usually just draw a dot. And therefore, if I add the 2 of them, there's the momentum of the total momentum initial, just that plus that. What does conservation of momentum say? Correct. This arrow will be identical to the final. So, in an elastic collision, I always screw this up every year, but there's no such thing as a perfectly elastic collision, it's just elastic. You'd expect the cue ball to stop. And therefore, what do you expect the 8 ball to do? In order to consume, yeah, there it is. The momentum of the 8 ball. Nicely, like I said, that's way too easy, so let's make it a little bit more challenging. Okay, let's say now I make the 8 ball. Let's say I make the 8 ball more massive. Okay, this would be exactly what you dealt with the very last example on your lab. Okay, if you make the 8 ball more elastic, the change in the cue ball would be much larger due to having a smaller amount of mass. This would be the equivalent, if you don't like the cue ball 8 ball example, okay, imagine Spainhour ran into a twin of Spainhour, okay, the first case, that would be like 2 cue balls being the same mass, okay, and then imagine that there is a sumo wrestler, gigantic sumo wrestler standing right over here that I want to move, okay, I run full speed and run into them, what do you expect me to do? Probably to bounce back a little bit. Okay? Why? Because my momentum will change easier. So, let's actually do that instead of the cue ball example. So here we are. We have the momentum of Spainhour initial. And this would be the momentum of sumo wrestler. Oh, come on now. Let's go teacher initial and sumo wrestler initial. So once again, there's the total initial, and that should be the same. I do that a little small. That should be the same as the total final. But at the end, you expect Spainhour, or the teacher, to be bouncing back this way. Yes? So what do you expect about the momentum of the of the sumo wrestler? They have to add to this to make this be the same at the end. So weirdly, the sumo wrestler has more momentum to the right in magnitude than Spainhour did initially in order to conserve. Does that automatically mean that sumo wrestler is going much faster than Spainhour? No, due to the fact more mass. More mass. It definitely can't. It gets weird in there. How are we doing here? Okay. Let's try a two-dimensional example. Let's go back to the 8-ball and the cue ball, because I think we do need that initial setup. Here's the momentum of the cue ball initial. Okay, and it's going to run into the 8-ball, which once again is just sitting there. So adding both of those up, we get the total initial. Okay? This time, rather than hit it dead on, let's say the cue ball is positioned up so that the 8-ball collides right here, right here. If it collides right here, we get Newton's third law. Newton's third law says there is a force of the cue ball on the 8-ball, and what's also going to happen? There's a force of the 8-ball back on the cue ball. If I just do a real basic analysis of acceleration, if the force on the 8-ball is going down and left, I expect two things to happen. Okay? The velocity was to the right. So if I break this down into its components, then the acceleration back this way in the x should force the velocity in the x to be smaller. Yes? But not zero, probably just smaller. And this acceleration down in the y should cause the cue ball to go downward, right? So I expect it to be going slower in the x and some amount in the y, which, if I'm not mistaken, puts it down in the 4th quadrant, right? So in other words, I'm going to use a different color for afterwards. Let's go with blue. Actually, hold on. I need to copy this first. And I still need to, is that the right color? No, close enough. So here's the final. So what I just told you was going to happen is I expect the cue ball to go down here. Less in the x, and some in the negative y direction. Now before I complete this, it is very important that you look at this situation and don't even necessarily do what I just did, but instead, what do you expect? What if you had a cue ball, what would you expect to happen? Okay, and I think without any sort of advanced math, I think you can tell me with this force right here, what do you expect the 8-ball to do? What quadrant do you expect the 8-ball to go into? First, of course. You expected the cue ball to go kind of down here and to the right, and you expected the 8-ball to go up there to the right as well. Yes? Is that what the conservation of momentum definitely says? Yes. If I take this momentum, all we are saying with two-dimensional momentum is that those two have to add to the original. The momentum of the 8-ball final. Now, the weird thing for people is to draw this here, okay? And I get that. So you kind of have to like see it in two spots. I don't want to make extra work for you, but I also want to make sure you understand what the heck it is that you're doing. So instead of drawing it here, imagine it over here, right? Isn't that exactly what you expect to happen? Don't you expect it to go up and to the right? Yes. Hopefully that's, but the way you show that conservation of momentum is that right there. What am I showing? I'm showing if I take the two individual momentums, okay? If I add the two initial momentums, I get the total initial. If I add the two final individual momentums, I get the total final, and these two are equal to each other. That visually is what I'm attempting to say when I draw this. The total initial is equal to the total final. And then if I break that down into their individual parts, this is here, this is here. If I add those two, I get the total. I get the total. The total is equal to the other total. The total is equal to the other total. And these two here must add to also equal that final right there. Questions, concerns? Okay. I've had a handful of questions about the lab. I will say this lab has produced good results in the past. I would say for the most part it produces good results, but there have been some cases where people go not too quick, but like it's hard to see whether or not it's a right answer. What I would suggest you do is look at like percentages of like how much they're off. Like use the initial as what you expect, not that it's better or worse than the other, and find percent difference. Percent difference is to say, I always hate when somebody just gives you a formula and doesn't explain what the heck it is you're doing. Like if I expect the number 8, okay, and I get the number 10, I'm off by 2. Okay, and I don't care that if it's 10 or 6. I don't care which way it's off. I just care that it's off by 2, right? This is what's known as just error. The amount that you're off is error. The way that you would find that is simply you'd make one of them what you expect. Sometimes there's an obvious answer, sometimes there isn't. Okay, usually there isn't. So let's just say in this case I was expecting 8. Okay, if I was expecting 8, the way I would get this is I would take the actual, the amount actual minus the expected. Okay, the difference between the two of them. You have seen this formula before. I'm just breaking down what it means. Okay, and I put an absolute value around it because do I give a crap whether it's positive or negative, above or below? No, that's just how much is off. The issue with just talking about error by itself, we could stop there. But if I said I was off by 2 in a lab, does that automatically tell you how well you did? Nope, because it doesn't give you any level of context, right? If I said I was off by 2 and the numbers are somewhere between 0 and 1, I'm off by 200%. That's a gigantic deal, right? But if my scale is 0 to 100, I'm off by 2%. I'm still off by the exact same amount, but the scale changes, right? On the other hand, if I was going from 0 to 1,000, 0.2%, that's stupid accurate in that particular case. So we need to give some context to how much it's off. So what we do is we take that difference, that amount of error, and divide by what you expected, What that does is essentially provides scale. In other words, I'm off by 2. How does 2 compare to the 8? It's about 25%. Okay? Now, understand that what I said earlier kind of changes things. There's some wiggle room here because I told you sometimes expected is not obvious. Like in this particular case, expected is which one's the right one? Which one can I put confidence in? Which one can I say is supposed to be the case? Who knows? Maybe it's the 10. And understand that if I choose the 10, does that technically change my percent error? Yeah, I give it a little bit more confidence by choosing that 10 because 2 out of 8 is 25%. 2 out of 10 is 20%, which means, so that is to say the conversation of error has some wiggle room here. There's not like an obvious answer. So what I would do is I would say, like I said, this number, I said for right now, make that your expected value. Find the difference between them, divide by it. And if you want, okay, this is going to give you a fraction. Some people don't like this, but like let's say I said earlier I do 8 and 2, I would end up with 0.25. That is a percentage, okay? That's just a percentage out of 1. So some people don't like that, so they always want to convert it to actual like percents by multiplying by 100. I usually don't, but if you want to, you can certainly turn 0.25 into 25% if you'd like. So that is to say, on this lab, the goal was to show that these two are in fact equal. So if you're doing your lab right now, you might be finding that they're not equal. Now I will tell you that I think the makeup data that I gave is pretty solid. Again, it's not perfect because it's a lab and there's certainly error and mistakes that are made. The biggest issue I'll tell you right now, and you can kind of spot when there should be a big error, is, for example, on the elastic situation. In the elastic situation, where you pushed the first cart into the second cart took off pretty crazy fast, yes? And then the first cart wasn't moving very much at all. The problem is with that guy right there, for the most part, because since it's not moving really fast, we want to measure that velocity. But the problem is it took, because it's not moving very quick, a large amount of time to get over to the second gate. What could happen to the velocity while it's moving over there to the second gate? What's that? It could decrease, or if you were weirdly on like a little bit of a hill, it could have actually increased beyond what it was supposed to. More than likely it decreased, you're right. But that could certainly cause some issues on this particular lab. Other question? Yes.
How is, like, can you talk about kinetic energy within, like, collisions?
Sure, I'd be happy to. Second hour asked me about this a little bit yesterday. I'm trying to do it in a way that I haven't done it before, because I don't like those teachers that just do that same thing 1,000 times and ask you to like understand the same way. So there was a problem on your homework that I think talked about like a group of flies, right? Do you remember what I'm talking about at all? Or maybe, I don't know, maybe there was. Okay, so maybe I'm misremembering. If I told you that there's 9 flies, okay, that are in an area, okay? If I tell you their total kinetic energy is 0, what does that mean individually about the flies? They're not moving. They can't be. The reason why they can't be is because since energy is scalar, if they are moving at all, they have some amount of energy. And since it's scalar, one energy cannot cancel another energy, right? If 2 flies are moving, you can't have less kinetic energy. It can only go up, only go up, only go up, right? So that means if there is kinetic energy in total, the group of flies, at least one of them has kinetic energy, so they cannot be moving in that case because the kinetic energies can't cancel. That being said, what does it mean if I have 10 flies and I say their total momentum is 0? Not necessarily. Unlike the last example, where kinetic energies can't cancel out, can you move and have momentums cancel each other out? Yes. Meaning, if I have two people of equal mass standing next to each other, if they're just standing here, you're right, that is an option, that they're not moving. But that's not necessarily the case. If the two of us want to start moving, okay, but don't want to have a total momentum, what do? We walk in opposite directions, okay? Now let's say it's me and that sumo wrestler again, okay? So we're not the same mass. Can we still cancel our momentums? Now the interesting thing about this is this. Yes, you got that. Like the sumo wrestler goes that way, I go this way. The sumo wrestler goes slower by a factor of however much bigger he is than me, right? So if we just make numbers easy, if I'm 1/2 of the mass of the sumo wrestler has to walk at 1/2 my velocity. Because of that, though, there is this interesting conversation having to do with center of mass. If you treat Spainhour and the sumo wrestler as one big object, okay, the combination. If you look at the center of mass, if we're just standing here, obviously the center of mass, the center between the two of us, should be a little bit closer to him because he's bigger, right? But if he starts going that way, at half the speed than I do, then center of mass doesn't move. If you think about that carefully, I'm taking 1/2 of the mass and going that way twice as fast. He's taking twice the mass and going half the speed that way. So the center of mass of an object doesn't actually move. And this is this weird, interesting thing that, like, if I took, gross, but for the sake of example here, let's say I had like a bomb inside of me that exploded, okay? And you somehow could track all the pieces of me and the velocities and all that direction and all that. More of me might go that way, but that means the less of me is going to go that way faster. Weirdly, if you could actually track all the velocities and pieces of me that hit and exploded, center of mass, if you calculated it, would still be in this exact same spot. Even when momentum changes, the center of mass stays in the same spot. So there's an interesting conversation if you play this all the way out. That means that if you look at the system of the universe, there has to be a center of the universe. Some pieces could be going faster that way, but that means they have less mass. Some pieces can be going slower that way, more mass. The center of mass of the universe is in one spot. Okay, to the other idea of that you could have been asking with kinetic energy. Okay, if I talk about collisions real quick, let's talk about the idealized situation and just hit them real quick. Let's make sure we're good on this because this should be elastic. What are the things you know about elastic? Kinetic energy conserved. Objects separate. There is no deformation in the objects.
What does that mean?
It means deformation is a word that basically means they are the exact same shape and they have not been changed. Okay? There is a reason why we talked about elastic force. We talked about it as spring force last chapter. Sorry, actually 2 chapters ago in forces. And then we talked about elastic force when we start talking about energy. The elastic force referenced in energy is the exact same elastic force that we're dealing with here in momentum. If you'll remember, back in energy, there was that big tree, right? And there was 3 types of mechanical energy, kinetic, gravitational, and elastic. And you knew there was conservation of mechanical energy if the only 2 forces could be gravity or elastic. So what we're saying in this chapter is, if the force is elastic, if the collision is elastic, mechanical energy has to be conserved. Well, if I'm looking at, say, 2 balls running into each other from a horizontal perspective, like I'm on a table right here, these 2 are running into each other, okay? Are they going to get more or less gravity? No, because it's the same height, right? When they collide, can that kinetic energy turn into elastic? Sure, they can bounce a little. But after they're done with the collision, what's the only mechanical energy that they could have? Kinetic. If you have a conservative force, if the force between them is perfectly elastic, then you would expect mechanical energy to be conserved. The only mechanical energy that is left, though, to be conserved is kinetic. So it's really an extension, if you will, off of this right here. Okay? The difference being the only one that's going to be there is that right there. I guess the other difference now being that these kinetic energies can actually be split between object 1 and object 2 to get all of the kinetic and all of the final. Now, what we then also said is if forces are non-conservative, okay, then we don't conserve mechanical energy, and some of that energy comes over into the non-mechanical spots, specifically focusing on sound, thermal. I remember if there's any other that I really want. Maybe light, but not really. Probably these two entirely. Meaning, if these two objects hit and there is deformation, they move from where they previously went, that means that they're not in the same spot and kinetic energy wasn't perfectly conserved. Now, how can you know this watching a game of pool? How can you know that it's not perfectly conserved? Is energy stolen by those two things? Do you hear pool being played? If you felt the pool balls after they collide, they should actually be a little bit hotter in that case, which means it's not perfectly conserved, which means some energy is being stolen, which means is it perfectly elastic? No. So let's go to perfectly inelastic. What do we know about perfectly inelastic? They stay together. There is deformation. They change. Kinetic energy is definitely not conserved. So I tried to show this to everybody when you were doing the lab, but it doesn't always work. Okay, I think my favorite example of this to understand the best, to see, to witness, and use that program I gave yesterday if it helps. Imagine I have two equal mass balls coming each other at the exact same velocity. If the situation is perfectly inelastic, what will they do? When they are done, they will stay together, sure. And what will their final velocity be? 0. Perfect demonstration. Is kinetic energy conserved? Well, obviously not, because we had some, and then now we have none, right? The numbers definitely don't add up where those could be the same on both sides. This is some number Sveinauer just made up, and this is 0. So kinetic energy decreased by 100 joules in that particular case. So it's not conserved in that particular case. Whereas on the opposite side of things, if this is an elastic collision, by the way, whether it's perfectly inelastic or elastic, 110% depends on what materials you're using, right? If these are two pieces of clay, you would expect this. And why do you expect that? Because you expect the force that the clay puts out to not be elastic. And do you expect clay to deform when hitting each other? Yes. Meaning, here's a simple put, does the clay go back to its original shape? No. So there's a simple way of putting it. On the other hand, if these are pool balls, do you expect them to go back to the original shape? So much closer to elastic. So what would you expect to, cue balls would never do a perfectly inelastic collision. What do you expect them to do? You'd expect elastic. If it's elastic and kinetic energy is conserved, what do you expect these two to do? Bounce off at each other at the exact same speed that they came in with, if it's elastic. Now there's elastic, like we said. There's perfectly inelastic. That's all the math you have. That's all I'm usually expecting you to get. But remember, inelastic is where everything is actually at. It is somewhere between the two. Are those pool balls actually elastic? No, it's a little bit less because you are going to get some kinetic energy conserved. But is it going to be close to elastic? Pretty darn close. That I would use that as your example. Okay. If I had two pieces of clay, are they actually perfectly inelastic? Do they actually go and not bounce at all? No, they definitely, if we look really close, will in fact bounce off each other just a little bit. That being said, if I had two toy cars, if I'm playing with my kid, he pushes the toy car and I push the toy car and they hit each other. Do you expect either one of these perfect situations? No. You don't expect it to be elastic because you don't expect them to bounce off at the same speed. You expect a large sound, right? You probably expect a little bit of deformation. There's going to be a dent or something somewhere in the object. On the other hand, it's definitely not perfectly inelastic. You never expect the cars to get together and just stick. There's a great video that Mythbusters did. If you want to watch it, I mean, you certainly can, but I think there's just a great demo of it. When they tried, the myth was there's two semis that came at each other, and there was a sedan or some little car that was fused in the middle of them. Okay, they hit so strong that it just fused in the middle of them. So they actually ramped up and got two semis to hit each other pretty darn close to full speed with a car in the middle. And no, it's 100%. It's like I said before, it's somewhere in the middle of the two of them. Do the semis bounce off each other? No, absolutely they don't. But do they perfectly inelastic fuse together and become one big mass? No, you don't expect that either. Other questions? Have we practiced with it? Go ahead.
So if, like, what would be like a good example of what's really difficult to ask? It's like, when you put, if it says, like, give an example of like perfectly inelastic, do you know what it would be like, all like perfectly just like,
Yeah, you get as close as you can. So elastic would be the cue balls sitting off of each other. Okay, this would be like, it's not perfect because there's not really like two tennis balls running into each other. Or even actually better than two tennis balls running into each other. Here we go. Probably elastic in that case. Why? Do I expect that particular guy to be at the same shape? These to be at the exact same shape? Yes. Okay. On the other hand, imagine where you going? I still need. No, you're not done today. Lazy butt. I get it's cold. None of us wanted to come. All right. On the other hand, okay. Oh, I got even better. I got to do it better too. If I threw something sticky at this, right? If I took like a glob of peanut butter, just threw it and smacked it to the side and stuck to the side. Okay. But even better than that, here we go. Cameron, take out your vengeance on me. You're going to throw it on my chest, and the first time I'm not going to catch it. Okay, you ready? Oh. That was bad. Okay, that was. Why don't we get a little closer? Okay, it's all right. Don't take offense to this. It's a matter of I'm protecting my electronics. Here we go. Okay, elastic for the most part. Okay, center here. No offense. All right. Anyway, center of mass. You wound up a little. I'm not that far away. All right. Don't miss on this one. Stand up. We're gonna play catch just so you can practice a little bit. Okay. Here we go. Thank you. Okay. All right. So here we go. All right. So I'm gonna walk at you now. Perfectly inelastic. Okay. All right. Why perfectly inelastic? Because the two objects, the mass and Spainhour, become one big object at the very end. So the same couple objects, same handful of objects, depending on what happens, could be closer to elastic or perfectly inelastic, depending on just kind of like me catching it, or humans kind of can change things a little bit more than inanimate objects. So does that answer your question? Okay. What else you got? Any other questions? Yes.
So impulse momentum theory is second law basically,
Yep.
the change, but is
Conservation of momentum is basically third.
okay.
And to that end, don't forget, technically, when you have a collision, you're technically always using both. It's just from a different perspective. So like we said the other day, let's say I had two objects that are about to run into each other in the middle of space. The other day, I think I used football players running into each other in this example. When they collide, there will be a force of 2 on 1 and 1 on 2, right? If my situation, if I look at just one, if I zoom in on one, which one should I be using? Impulse momentum theorem. What easy thing can you look at to let you know that? There's a net force. There's a net force on the system that you looked at, okay? But if instead I look at the combination of two of them, is there a net force anymore? How come? What did this third law pair do to each other? Cancel each other out. So there is no net force anymore, and therefore we can use conservation of momentum. Okay. Similarly, if Spainhour cut off his arm, okay, and tossed it across the front of the room, if you just looked at the leftover bit of Spainhour, not his arm, it would be this, because Spainhour's arm is causing a force back on Spainhour, so there'd be an impulse that way. You'd see him change momentum that way because the second part of him went that way. If you just look at Spainhour, his momentum would change. If you look at the Spainhour arm combination, then it is conserved. The total of Spainhour's mass has not changed. If I'm standing here in front of you and I throw my arm that way, individually you'd see the arm go that way, you'd see me go this way, but the total of me is still in that exact same spot. To prove that, here I will do it without detaching my arm, because that's a little bit morbid. Why can't I move myself like that? Excellent question for tomorrow. Why can't you move yourself in space? Be a little bit more specific, but I'm with it. What can't?
The force you input out, it just comes back, so it's just you.
Here's how I would do that if I were you. I would still separate the objects, even though obviously they're not staying separate. The force Spainhour puts on his arm. Okay? It's going to go that way. Absolutely. I'm putting a force on my arm to go that way. But what must be the case? The arm puts a force on Spainhour that is equal and opposite, and since I'm all attached, these two forces on the same big object will cancel, leaving us with a net force of 0, so you can't cause an object. Questions, concerns?
So I saw that this is a quest. So is that
It's not, it's a test. It used to say quest on here. I didn't change the wording on there, I apologize. That's when it was a really quick thing at the end of the semester. It's not now. There's a little bit more space for it, so it is a test. I think I'm not going to do a full tutoring session tonight, like an hour-long thing, but I am going to be here after school if you had any quick questions that you would like to get answered individually before tomorrow.